Okay, everybody, we're back to talk about more about stochastic processes and such. We will start today looking at the homework. So let me go ahead and look at the homework. Let me get the homework up here. What happened to the homework? I had it up here. I guess I closed it. Silly me. So let me do this and go here and open a bunch of screens and click a lot. And there's the homework. Okay, so I'm ready to share my screen. Okay, here is the homework last time. This was last time, so we've already done this. No, we haven't done that. We haven't done the confidence intervals as of yet. Okay, so this is the one we have to do. So let's start first of all with confidence intervals. The first confidence interval is out of 10,000 tries, a ball rolls into a green slot 735 times. This is on a roulette wheel that has 37 slots. So generate a 95% confidence interval around the sample average of 0.0735, which is this number, the 735 with the decimal moved over a bunch of times. So let me get my coins here, and let's assign number. Adam, you're zero. What's that?
I can do number one if you want.
Well, let's do Adam 0, Matthew 1, Justin 2, and then Glauco 3. Is that okay? Okay, so here we go. Okay, we got heads. That's 3. Glauco.
Okay, I'm going to share my screen, but you have to enable it.
I have to do this, and I have to allow you, since I am the omnipotent overlord of Zoom, I can let you share your screen now. Okay.
Okay, so as it is repeated, we can apply, assume that it's Gaussian because it's a lot of repetition, so
yes.
it converts to a Gaussian.
Yes.
I follow in the slides. I generate the confidence interval with this formula.
Yes.
So this is the number you have to add to the probability and to subtract. And as the value 2/37 is much lower than the lower bound for the confidence interval for 95%, which means that we know for sure that not for sure, we are 95% sure that the probability lies within this interval. So this number is far away to the left. So probably the roulette wheel is unfair.
Okay, 0.735. Yes, but let's see. I have not worked this problem, so I'm looking at the numbers for the first time. You had the upper limit is 0.0786, right? 15.
Right.
And the sample average is 735 or 0.0735. Doesn't that lie within this interval?
But the interval is booled for the observed probability. The observed probability is P.
Yes.
So we bool this interval around this
okay.
number.
So this is the true probability down here, 0.054054. So what you're saying is that does not lie within the confidence interval.
Yes, that's what I mean.
Okay,
yes.
okay. Okay, wow, that's interesting. So if you did this statistical test, what would you do? You might bet on everything that isn't green, huh? Or would you bet on everything green?
I will
Bet on
bet in
everything
green. Yeah.
You would bet on the
I
green.
just looked it out real quick. If you have that confidence interval there, that means there's somewhere between 2.5 and 2.9 green spaces equivalently.
Oh, okay. So you worked it backwards.
Mm-hmm.
Okay. Okay. So that tells you how to bet, right?
Yep.
I wonder, and I don't know, but if you remember Claude Shannon and one of his colleagues at Bell Labs went to a casino and bet money on the roulette wheel. I wonder if they did something like this. I have no idea. But it's kind of compelling, isn't it?
It makes sense if the odds are greater than the multiple of the, if the odds and the multiplier of the money don't match.
Yeah, that's interesting. Okay, thank you. Thank you, Glauco. Okay, cars go by at a point on University Avenue at an average rate of 1 car every 2 seconds. What is the probability no cars go by in 1 second? This should be a very simple problem for you. The more interesting one is, I'm looking around for my coins. Oh, there's my coins. Okay. The interesting one is problem number 2. No cars go by for 5 seconds. What's the probability no cars go by after 6 seconds? That is 1 second more than 5 seconds. Okay. Oh, we got 3 again. Okay, now we got 0. So Adam, you are up, and I'm going to let you share your screen. By the way, hold on, I write down how you do on these things, so I need to do that. Go ahead, Adam.
Please excuse my mess. I'm going to rewrite this all nicely, but it's on scratch paper at the moment. So we're given that there is 1 car every 2 seconds. So that means that the mean is half a car every second. So then we use the formula here for the Poisson counting variables. And we want k to be equal to 0. So saying no cars pass and t equals 1 second. So we plug into this formula here, and we get 0.60653 being the probability that no cars would pass in 1 second. I also, for fun, went and figured out what the probability of 1 car passing in 1 second is, and that's 0.303, 1/2 of that, interestingly enough. But then the second half of the problem, things get a bit more interesting. So we want to know what the probability that after t1 seconds there were I, and then at a later time, t2, there were j. So then that's the probability of the first case happening after t1 seconds there were I times the probability that in the intervening period there was the change. So then you can follow this math down, and then you plug in this formula here that we had up here. And then we plug in all of these numbers here. So we say it wanted that after 5 seconds there had been 0. So we wanted the probability that after 6 there would be 0. So we plug in those again. And it works down to just multiplication of these 2 exponentials here. So 0.049787.
So why didn't you just put in 6 seconds?
Because it was, I guess you could ask, no, it would be different. Because we're basically asking for the probability of 6 given 5, which would be slightly different than just the probability of, yes, that would be different than the probability of 6, because it's only dependent on that next one. It's not only dependent on that next 1 second, but it is dependent on that next 1 second, as opposed to looking at all.
Well, if
I'm not articulating this well.
Okay, did anybody else get a different answer than this?
I got the same answer, but maybe some more rationale is you can't
Let
just
me,
do.
let me go back. By the way, stop sharing your screen just for a second here, Adam. Thank you. I want to make sure of something. The way that this is worded, what I meant it to do is, what is the probability that no cars go back after 6 seconds given, not and, but given that there's been no cars in the first 5 seconds?
Yeah, I did differently.
So I wanted a conditional probability here. Did anybody try that way? Glauco, did you try that way?
Yes, I did it a different approach. Yes.
Okay, let's see what you did. Maybe there was some ambiguity in the statement stating of the question, but my intent was to have that it was a conditional probability. What's the probability that no cars go by in 6 seconds, given that no cars have gone by in 5 seconds? As a conditional probability. Go ahead.
I cannot share the screen. Can you stop sharing, please?
Oh, yes, I can. I can do all things.
Okay. The first part of the problem, I work it differently, so I got a probability of 1/2.
Okay, let's talk about why you went. So you were taking not the Poisson process, but the binomial that had the Poisson process. Okay, I'm not sure I like that, but go ahead.
Okay, so from that part, I did the second one and I got 1/2. That is the same.
Okay, well, the spirit is right, but the answer is wrong, I believe.
Okay.
You should have used the Poisson here. That was the whole point of the problem. It was a Poisson random variable.
Okay.
And go ahead and stop sharing your screen. If you remember, when Adam did his first solution, it was the probability was e to the minus what? Lambda t, right? Where lambda was, what did I say?
Lambda's 1/2.
Okay, lambda's 1/2 and t is equal to 1 second, right? Now, in general, it's going to be e to the lambda t. What did we remember about a probability density function of e to the minus lambda? It has no memory. Do you recall that? It has no memory. So therefore, if you're sitting there for 5 seconds and no cars go by and you want to wait for the next second, it's just like the clock restarts. It's just exactly like the clock restarts, just like the exponential random variable. Did anybody get that?
I think that's what I have.
Well, it should have been the same as for 1 second.
Oh, so just the probability that that next 1 second is 0, not the probability that you had 5 and then the 1.
Yes, it was the probability that's 6.
Okay. So I had done it like that, but then I found a equation in the book that I thought was more accurate, because I was thinking like that's like the ageless exponential that we had talked about, but I thought the Poisson process was different, so I actually did it a different way.
It is. Well, the interesting thing is if you take the Poisson process and you talk about the probability of no occurrences over an interval of time, that turns out to be an exponential random variable. And just like an exponential random variable, it has no memory. Remember us talking about that a long time ago when we talked about conditional probabilities? That's the same thing that happens here. It's an exponential random variable. And if you have no occurrences, it's just like the clock resets. In fact, the clock always resets in the Poisson process, and your future events are totally independent of your past events. Your future events are totally independent of your past events. So in this case, since in both cases it was the chances of 0 cars going by, both of the answers should have been exactly the same. The math should have worked out exactly the same as the exponential random variable when we looked at the conditional probability. So I'd like you to look at that and look at that a little bit more closer and see if you can generate the answer that I gave. and show me that I'm wrong if I am wrong. Okay. So that is a very interesting process about the Poisson. And if you think about the Poisson, what happened in the past, if you just think intuitively about it, what happened in the past is going to have nothing to do with what happens in the future. What happens in the past has nothing to do with what happens in the future. So we could have had 20 cars go by in that 5 seconds, and the probability a car would go by in the next second would be the same. It doesn't matter. They are independent. Okay, let's look at this next one. I thought the next one would be a little bit hard. We'll see. A sequence of IID uniform random numbers is on 0, 1. It's convolved with a rectangular window of length 100. Call the resulting stochastic process X. Calculate the mean autocorrelation and autocovariance of X. We only have 2 people left. Let's see. We have Matthew and Justin. Is that right? Matthew and Justin. Okay. Matthew, your heads. Justin, your tails. Okay, it's heads. Matthew, did you get this one, Matthew?
Yeah, I admittedly did not get this one. I tried to work it in MATLAB, but things were just not making sense to me.
Okay. Did anybody? Okay, let's see. Justin, did you get it?
I also tried it in MATLAB. I did it. I really didn't get far with it. I implemented it and saw that like the distribution for C does go to Gaussian. You know, just the one convolution goes to a triangle function, and if you continue that, that would approach Gaussian. That would be defined by the central limit theorem. But I didn't make it far beyond that. I did have some thought about that. You could define it as like an LTI system, and we know that that LTI system is White's and stationary, but I didn't make it far on that. And
well, that's interesting. In fact, when we get to the processing of stochastic signals, wide sense stationary stochastic signals, this problem should be very easy to solve. And what did you identify the autocorrelation looking like?
I didn't get.
Oh, okay. I thought you said a rectangle or no, a triangle or something.
I just had for the stochastic process X when you do the convolution between.
Oh, I see. I see what you're saying. Okay. Okay.
Yeah, it was like a triangle, and that's kind of approaching a Gaussian.
Okay. Is X stationary in the wide sense? Well, we're having a little bit of problems with these, aren't we? That, you know, that's okay. We want to identify that a little bit more closely. And then lastly, is X Gaussian or close to Gaussian? And I think you alluded to that, Matthew, didn't you? That you thought it was pretty close to Gaussian?
That was me.
Oh, that was Justin. Okay. Okay. And why did you think it was pretty close to Gaussian?
I mean, MATLAB kind of verified it, but you know, you're convoluting 2 different uniform distributions basically, and by the central limit theorem tells you that that's going to approach a Gaussian. Okay,
a little bit of English correction. You never convolute 2 functions; you always convolve them. Okay.
Convolve them. Okay.
Yeah, convolve them. We don't convolute. That sounds like an Appalachian engineer. That's what they would say. Okay, let's see. Calculate the mean and autocorrelation of the autocovariance. Let's put that on hold for a while, because I'm going to expand this a little bit next week. And I am going to ask you to do something, which is to actually explain how you would estimate the autocorrelation of a stationary random process. And I would I would suggest that you do an ensemble. Do you remember an ensemble? This will be computer work, and you generate a sequence of stochastic processes that are, first of all, IID and just white, just independent random variables on 0 to 1, convolve each one with a rectangle function, and then look at that ensemble of stochastic processes in some way come up to estimate an autocorrelation function. I will give you a hint. It turns out to be triangular. It does turn out to be triangular. So you should get this for triangular. And possibly if you work this, it'll give you a better idea of how to compute this analytically. And that's eventually what I would like you to do, is to compute this analytically. And we might get in to the analytical aspect of that today. Well, maybe we can talk about this a little bit more. Okay, so let's talk about this a little bit more in terms of how we might do this. We will start out with a random variable. Where's my pen? How come my pen isn't working? Unplug it and plug it in, and there it is. Okay. So we have a value of x, if you will, of n. And that's equal to a sequence of numbers. And all of these numbers are between 0 and 1, correct? We're going to assume that it's wide sense stationary, so this thing goes on forever and ever and ever, both in negative time and in positive time. So that's what this is. So what is the autocorrelation? What is the autocorrelation of x? Let's do n and m at two different points. So we're computing the autocorrelation between 2 points, n and m. And that autocorrelation is assuming, well, since it's real, we don't have to worry about conjugation. That's equal to this result, right? Now, if indeed the process is stochastic, the expected value of x sub n and m are going to be independent if n is not equal to m. So it's equal to the expected value of x sub n times the expected value of x sub m. That's true if what? If they are independent of each other and n is not equal to m. If n is equal to m, then this is the expected value of x squared of n, correct? Now, in order to do this, I should have worked the first problem here. And the first problem is, what's the expected value of x sub n? Can you tell me what that is? These are random numbers from 0 to what? 0 to 1. The expected value is 1/2, correct? That's kind of obvious. So this then is equal to 1/2 squared if n is not equal to m. And what is expected value of x squared? In other words, what is the expected value of a uniform random variable between 0 and 1. It's equal to the integral from 0 to 1 of x squared dx. Let's see, is that right? Expected value of x squared is equal to the integral of x squared times the density function, right? And the density function is equal to 1/2 over the interval from 0 to 1. Is that okay? The probability density function here for each one of these random variables is a uniform random variable between 0 and 1 with a height of 1, correct? So where did I get the 1/2 from? I don't know. I don't know. It shouldn't be there. So this is equal to 1/3 x cubed between 0 and 1. So that's equal to 1/3. Is that right? Yes. So it's equal
Yes.
to 1/3 for n is equal to m. Okay, so that's just working out the statistics for the first random variable. Now we're going to set up the second random variable, y sub n. Well, let's call it y sub, let's use a script L. Why not? We're just going to do a summation from n is equal to L plus, what do we say, 5? How long was the window?
100.
100. Okay, L plus 99. Because we're starting at 0 here. Of x sub n. No, I'm sorry, x sub L. Yeah, is that right? Yeah, n is equal to L to L plus 99. Do we agree with that? So
Shouldn't there be some sort of factor in front to scale?
I think we added them. We're not averaging them.
Okay.
Is that right?
I see. Yes, we're talking about adding everything in the
Yeah, we're
rectangle.
just adding them. So what is the expected value of y? Well, that's equal to what y sub L. That's equal to the expected value of summation of n is equal to L plus 99 of x sub n, correct? And what is this? This we decided was 1/2. So it looks like this is going to be 100 over 2. So that makes sense, right? And then what is the autocorrelation of y? Whoops. Let's use P and Q here. That's going to be the autocorrelation of y at the points P and Q. Now, I don't plan to work all this for you, but it's a matter of substituting this into this result. And turning the crank. And out should pop the autocorrelation of y. And it should be stationary. If you do this right, this should be just a function of P minus Q. So hopefully that gives you a running start towards the analytic solution of this. I've done the easy parts, but hopefully I've given you some runway on which to take off. Okay. So for next time, I'd like to talk about this problem, the sequence of IID, uniform random variables. And then secondly, I would like to talk about this new result, which I'd like you to generate by computer. And that is estimating the autocorrelation from an ensemble. If you look back in your notes, we showed how to do it. If you look back in your notes, we showed how to do it. Now, in computing this autocorrelation, I think it's going to be simpler for you if you decide that the autocorrelation corresponds to a wide sense stationary system or process, I'm sorry. So it's a wide sense stationary stochastic process. And so I would like you to, first of all, explain it. This is in previous notes. And then I would like you to do computer work to do this empirically, and just to show that your empirical results from the previous homework are indeed valid experimentally. Any questions on that? So we'll talk about this the next lecture, any questions that you might have, and then let's have it be due 2 lectures from now. Okay. And I'd also like you to get this Poisson counting, well, let's see. The roulette wheel and the cars go by the Poisson process. I'd like those to be submitted today, if that's okay. I tell you what, because of illness in the family, let's have this due tomorrow. Tomorrow at close of business. Okay? Tomorrow at the close of business.
Thank you.
I have no idea what that means, by the way. What does that mean? 5 o'clock? Yeah, something like that. Tomorrow by midnight. I don't care. I won't be looking at them tomorrow. So. Okay, very well. Let me get up then the lectures for this time. And I'm not sure which one I want to do. Let's do the Gaussian. This is we're going to put the Gaussian off for a second. One of the things I wanted to show you that if a Gaussian is stationary in the wide sense, it's also stationary in the strict sense, which is a pretty cool result. So let's review what we talked about last time and hopefully go on a little bit. This is what we did last time. We said that if we perform a Fourier transform on the autocorrelation, we get the power spectral density. And the inverse transform of the power spectral density is the autocorrelation. And the reason we use this is spectral is a function of frequency and power density is integration gives you power. So that's the idea of power spectral density. You know what? I put down my magic pen here and I can't find where I put it down. I think I have a pen that wants to escape my attention. There it is. Okay. So I like to put little check marks. I know that it's hard to follow my cursor, especially in the recording of it. So here is the inverse transform of the power spectral density. This again is only applicable to stochastic processes that are stationary in the wide sense. Now, one of the things that we figured out was that the area under the power spectral density, since the power spectral density is given by this, If we evaluated this, if we integrated over all of this at tau is equal to 0, tau is equal to 0 would correspond to setting this exponential to 1. So if we look at the autocorrelation at the origin, we just get the area. This is a fundamental theorem of Fourier analysis, that if you just want the origin of a function, you can look at the Fourier transform and do what the things that we've talked about here. So this being the case, we have that the area under the power spectral density, my pen quit working, daggone it. Come on, you silly pen. Okay, there we go. I think we got it. No, we don't. Okay. You know what? It might not be my pen. It might be. Let me attend to my technical difficulties here just for a second, hopefully. Okay. I'm going to have to revert to using my substandard headphone microphone. Can you hear me? Give me a thumbs up. Okay, you can. Okay.
Yes.
Okay, so then last time we went through some of these applications. We just did that. We looked at some of the properties. One is that the area of the power spectral density is the power. So this really relates to why we call it a power spectral density. Okay, what's going on? Okay, well, my goodness, technical difficulties. So the area under the power spectral density is the average power. So if you give me a power spectral density, now my pen's starting to play games with me. If you give me a power spectral density as a function of frequency, this entire area is equal to the average power. And can you see that the idea of the power spectral density all of a sudden becomes apparent? Because if we do have a power spectral density and we would like to know the frequency content of the stochastic process between, say, these 2 points, we simply take that area, and that's the percent of, well, it's the total average power in this interval. from lower to an upper bound. Now, because of the weirdness of the Fourier transform, we have to take a symmetric value here, which we also mentioned last time. So it's twice the area from the lower to the upper bound. We can do twice the area because as you can see here, the power spectral density is even. The other thing is that it's real, but even more important than real, it is non-negative. It is always greater than or equal to 0. So we can never talk about a stochastic process having negative power or anything of that sort. So these are the properties of the power spectral density, and they're relatively intuitive. What is not intuitive still to me is that this is the Fourier transform of the autocorrelation. That's pretty cool. Oh, by the way, I will say that the proof to follow, we'll get to a point where we can literally prove that it is non-negative. It's pretty easy to do it, but we need a little bit more background to show this. Okay. Okay, the density, the power spectral density is even because R sub x is even. In the more general case, if you remember, R sub x of tau is equal to R sub x of minus tau. And if indeed you have a complex stochastic process, there's a conjugate here. But still, we're good. So therefore, we can always write the real part as the power. Okay, because R sub x is real, it's even. So therefore, we can throw away the j sign, right? It's equal to R times e to the plus j. I'm sorry, time cosine plus j sine. This is going to be even. This is going to be odd. I think we did this last time. This is going to be odd. And even times odd is odd, and it's going to integrate out to 0. So therefore, we can take the real part under the assumption that it is real. If x is real, then it's instead of the e to the j, we can just do the cosine. And the other thing is that this is even and this is even. If you have an even function, then the integral from minus infinity to infinity is the same as twice the integral from 0 to infinity, right? So this is another way that you can do this if you want to simplify it. And you notice that there's nothing in this expression that is complex. It's always real. The power in a specified frequency band is obtained by integrating the power spectral density. So if we have a band in the interval, for example, from minus b sub L to b sub L, b sub upper, lower and upper, and we have some sort of power spectral density here, then the power that is in this frequency band is equal to the area of this. But again, you have to do the negative frequencies, so you also have to take this mirror image, but this area is going to be exactly the same as this area, so it's simply twice the upper positive frequency value, so it's twice this integral. And so that's how you find the power in a specific frequency band. Let's look, for example, at the random telegraph signal. If you remember that, we had some Poisson points. We chose the origin. We chose the origin as a flip point, so it could either be plus or minus 1. And if we did that and we had some Poisson points, these things came along and did something like this. Where the transitions occurred at the Poisson point. In that case, whoops, wrong one. This is e to the minus, so this is a or the first one was a bipolar. This one is binary, so it just goes from 0 to 1. It's e to the minus 2 alpha tau. You'll notice that it is wide sense stationary. And if we want to take this random telegraph signal and we would like to convert it into a power spectral density and figure out the power associated with some bands, we can first of all take the Fourier transform. The Fourier transform is given by the expression, which is covered up a little bit by my red scribblings here. It's kind of a Cauchy shaped power spectral density. And then if we would like to compute the frequency or the amount of power in those frequency bands, here's the general formula. It's twice the integral from the lower to the upper bandwidth. And so for our specific case of the random telegraph signal, it's equal to twice alpha. Now you might or might not remember, but this thing integrates to an arctangent. It integrates to an arctangent. And so what we get is we have the arctangent of the upper limit minus the arctangent of the lower limit with a little bit of finesse. Hopefully with your background in calculus, you can do that. So that is the amount of power in the random telegraph signal that exists in the lower to the upper limit. We can also talk about the power spectral density of a discrete time signal. And anytime we store a signal on a vector analyzer or MATLAB or whatever, it's discrete, right? It's a big vector. And so we can always treat this as a discrete time stochastic process. And the power spectral density is now not the Fourier transform, but the DTFT, discrete time Fourier transform. Of course, we know in engineering that we use the FFT instead of the discrete time Fourier transform. We use an FFT because that's a little bit quicker. This is if you want your sample power spectral density. You see, there's a number of different Fourier transform. If you have a continuous to a continuous, this is a Fourier transform. If you have a continuous to a discrete, this is a Fourier series. If you have a discrete to a discrete, if you have a discrete to a discrete, that is the FFT, or the discrete Fourier transform, or the FFT. And then if you have a discrete to a continuous, notice we have all four things covered here. Then that's where you get a DTFT, discrete time Fourier transform. But of course, you can get this DFT by sampling the discrete time Fourier transform. But don't worry about that. We take the discrete time Fourier transform of the autocorrelation. So it is a discrete to continuous mapping in the Fourier domain. And whoops, my goodness, I wrote all over that. Let me get rid of some of this stuff here. No, it's not letting me do that. Let's see if I have an eraser. Oh, it says clear all drawings, clear my drawings. Okay, it's not doing this. You might not be able to see this because of my non-anticipatory scribblings, but this is e to the j2 pi fn. Now, if you recall from signal processing, f no longer has units of frequency. What are the units of f? Can anybody tell me? I will give you a hint. This exponent has to be unitless, doesn't it? I mean, what's e to the j 3 feet? It makes no sense, right? It has to be e to the j something which is unitless. Since n is unitless, f is unitless. That's the reason that we have the discrete time Fourier transform always on the interval from -1/2 to 1/2. Now, you might have remembered it from something like from -π/2 to π/2. But this is something like this. And so you always have a repetition here. How do we know it's periodic? Because this guy right here is nothing more than a Fourier series. That's a Fourier series. And what are the Fourier series coefficients? They're the autocorrelation function. So because this is a Fourier series, this thing is going to be periodic. It's the Fourier series of the power spectral density. So S sub f has the power spectral density properties, except integration is from -1/2 to 1/2. And like all discrete time Fourier transforms, the power spectral density is periodic with a period of 1. Again, you might have seen it from -π/2 to π/2. That's when they used omega. People use omega in the discrete time Fourier transform. I am not a big fan of omega, because I don't know what something vibrating at 62 radians per second means. I know what something vibrating at 400 cycles per second means, or 400 hertz. I understand that, but not 300 radians per second. So I like to use F. And when you use F instead of radians per second, you get periodicity from -1/2 to 1/2. Let me try something here. No, I'm not going to try it. Okay, so this is all well and good. Okay, I am going to unshare my screen. Guys, my unshare is not here. Okay, there we go. I finally got it to work. Now there's different types of white noise, or there's different types of power spectral densities corresponding to different types of noise. And some of these you have heard of. One is white noise. Now, white noise, if you know about light, light contains all of the frequencies. So if we look at the frequencies and we look at the power spectral density, white noise contains all frequencies, all frequency components at the same exact level. Again, since all frequencies are equally present, that's the case with white light. So this is referred to as white noise. There is discrete white noise. Discrete white noise, we said, was, well, anything discrete is periodic with an interval from -1/2 to 1/2, right? So if we replicate this -1/2 to 1/2 and we just keep it uniform, it also looks like it has a total power spectral density across all frequencies of the constant. But again, we're typically just interested in the values between -1/2 and 1/2. Then there is Laplace noise. Laplace noise would have, well, it would have like an exponential, a double-sided exponential as the power spectral density, since that's what Laplace is. Let's spend a little bit of time about talking about continuous white noise and why there's some sort of problems with it. one of the problems with it is that if we were to look at the power spectral density, which is a constant, as typically denoted by the constant as n naught over 2, n naught is the noise level, then the inverse Fourier transform of a constant is a Dirac delta. Do you recall that? It's a Dirac delta. So this is all well and good until you start to say, okay, there might be some problems with this. And one of the problems is do you remember what the average power was?
The integral of the power into, yeah.
Yeah, it's equal to that. So for white noise, what's this equal to?
Would be infinite, wouldn't it?
Be infinite. To generate white noise requires infinite power. Why do we use it? Infinite power doesn't exist, right? David Hilbert says infinity is nowhere manifest in our universe. Everything in our universe is finite energy. Everything in our universe is finite. There is no infinity. There's conceptual infinity, but there isn't the actual true infinity. Well, we use it because it gives us a lot of analytic mileage. Let's look what this means in terms of the autocorrelation. If we have an autocorrelation and we have white noise, and we kind of have an idea what white noise sounds like, right? There can be different types of white noise. But it says if you take any point here, say x of t, and you go out just a little bit, that this point has to be uncorrelated with this point. That means you have to have a lot of ability to move up and down with white noise. And that ability to move up and down instantaneously requires an infinite amount of power. Okay, well, that's not good news, right? But nevertheless, we use the concept of white noise all the time. We use it because of its analytic tractability. Remember, our Gaussian is our good buddy in probability and statistics. Well, white noise is our good buddy in dealing with stochastic processes. It's so easy to deal with analytically. So we have this continuous white noise, and we have thermal noise. Thermal noise is almost white noise. You have frequency, and thermal noise comes out and it's flat for a really, really long time. And then it begins to taper off. So eventually, this area under the power spectral density is going to be finite. But you can see that within this interval here that it looks pretty white. So thermal noise is our excuse for using white noise. There's other manifestations of white noise too. As we mentioned, this takes infinite power, and that's no good. Now, let's deconstruct what we mean by white Gaussian noise. What is white Gaussian noise? Number one, it means that the autocorrelation must be a delta function, and that the power spectral density is uniform. What does it mean about Gaussian? It means that if we take any points here, say this point and this point and this point and this point, and we perform a four-dimensional probability density function on these 4 points, that probability density function will be Gaussian. If it's wide sense stationary and we move these points, then the results here also have to be have the same probability density function if it indeed is white. We will talk more about this in a proof which I'm going to give you, is that if a Gaussian process, a Gaussian probability density function, or a Gaussian stochastic process is wide sense stationary, it's also stationary in the strict sense. I mentioned this before, but it's worth mentioning. Usually stationary in the strict sense implies wide sense stationary. However, for a Gaussian, strict sense stationarity implies wide sense stationary, but the converse is always also true. The arrow points the other way. It isn't obvious yet, but we will show that eventually. So again, this is important, white Gaussian noise, because things are happening in two different areas right now. One is the spectral domain. That's the Fourier transform of the autocorrelation. The second one is in the probability density function of the stochastic process. This is x of t. So we have to talk about the up and down, if you will, probability density function for the stochastic process. The up and down motion is the Gaussian part. The Fourier transform of the autocorrelation is the white part, the white Gaussian noise. Okay. Now, discrete white noise is a little bit different animal, because the autocorrelation for discrete white noise is equal to the second moment times a Kronecker delta. Now, Kronecker delta, if you recall, is equal to 1 for n is equal to 0, and it's equal to 0 for n not equal to 0. It's the discrete equivalent of a Dirac delta. But the interesting thing is that the power spectral density is x bar squared, but that power spectral density only exists and is only applicable over the frequency range from -1/2 to 1/2. Yes, if we replicate it, we do get a constant. If we do replicate it, we do get a constant, but we're only interested in because it's discrete over this interval. So the overall area here, or the overall power, is just equal to the integral of this of the discrete time Fourier transform over the interval from 1/2 to 1/2. So that's finite. So it's a little bit different animal. Discrete white noise has finite power. Continuous white noise has infinite power. And as a result, you cannot sample continuous white noise and get discrete white noise. You think you might be able to, but you come out here, and if you sample this white noise, the autocorrelation is a Dirac delta. And you cannot sample this continuous white noise and get discrete white noise. Now, discrete white noise, by the way, I should mention, well, let me go through this slide. Discrete white noise is an IID sequence. That's discrete white noise. It does have finite power, and you cannot get it from samples of the continuous white noise. By the way, there's other white noise other than Gaussian white noise. The power spectral density does not dictate any of the probability density functions of the underlying stochastic process. You can have Laplace white noise, you can have Cauchy white noise, you can have all sorts of white noise. The whiteness is a function of the autocorrelation, right? And that autocorrelation can occur if your underlying stochastic process is Gaussian, Laplace, or some other sort of random variable. So I think that that concludes this. So what we've done is we've looked at the power spectral density, and we've seen that it's very intuitive. Many of you have already in your laboratory work come up on power spectral densities. But now we can relate it back to the original time series, recognized as the Fourier transform of the autocorrelation. So if you do have the power spectral density, you can inverse Fourier transform it and get the autocorrelation. But the interesting part of the of the power spectral density is you can get how much power is in a frequency band by integrating over the power spectral density in that frequency band. Next time, we're going to do something really interesting. We're going to look at filtering stochastic process, wide sense stationary stochastic processes. What happens if you take a stochastic process and you run it through a low pass filter? Suppose that you know the autocorrelation, power spectral density, same thing, and the mean of the stochastic process that's the input. So the input, you know the mean, you know the autocorrelation, you know the power spectral density. Can you, if you know the impulse response of the time invariant signal, compute the power spectral density and mean of the output? And yes, you can. And that's the beauty of looking at wide sense stationary stochastic processes being fed through linear time invariant systems. So notice we have things not changing in two ways. We have the signal not changing with respect to time. It's stationary, right? Its characteristic stays exactly the same. So that's number one. And secondly, we have a system that doesn't change with respect to time. That's what the time invariance does. And when you put the two together, we can get really, really interesting results, as we'll look at next time. Okay, with that, are there any questions at all? No? Okay, so work on those problems and hopefully you'll be able to get them by next time. Or I know, I tell you what, let's not, they're not due next time. We want to talk about them next time and have them due a week from today. Okay, that I misspoke. Okay, thank you very much, guys. We'll see you. Take care.
Thanks, Dr. Martz.